Sure. Okay, yeah, pretty small class. But anyways, welcome everybody. We are going to be covering Ramsey's theorem. So, all right. So first we're going to go through like the basic version. That's trends and strangers. We're going to state the full theorem. Then we're going to look at what I hope is going to be like the more interesting stuff for you guys, which is calculating the Ramsey numbers. This is actually where the most of the work is. And then some other stuff that you guys can explore. So suppose 6 people walk into a party. Like we actually have 6 people right here. So I can guarantee that either 3 of you guys all know each other or all don't know each other, right? Probably know each other, since you guys tend to come pretty often, but that's something I can prove. And question is, how do we prove this? How do we represent this? Anyone have any ideas? On to. All right. Also, okay, yeah. All right. We are going to be coloring the edges graph. So what that means is that we're going to mark off each of our each people in the party as a vertex. And we draw all the edges between them. Each edge kind of tells us something about their connection, right? And the way we're going to represent this is either 2 people know each other or they don't, right? So if they know each other, we connect them with a red edge. If they don't know each other, we connect them with a blue edge. And as you can see here, this is just one of the many possible ways that this could look, right? Frank here, he's all blue, he doesn't know anyone at the party, unfortunately for him. But we can already see here the property that we're looking for. So we have Alice, Bob, and Eve. They all know each other because they're all connected to each other with red edges. And we also have Carter, Denise, and Alice all don't know each other. They're all connected with blue edges. So how do we prove this? All right. Well, so yeah, here's the form theorem. In a group of 6 people, there are either 3 who know each other and 3 who don't know each other. Also, feel free to stop me if you have any questions. We're going to start moving into the proof of this. And formally, and this is where we're going to bring in some terminology. K6 is the complete graph with 6 vertices. And what a complete graph means is that every single vertex is connected to every single other vertex, right? So if we color the edges of a complete graph K6 with 2 colors, the standard is red or blue. That's what we're going to be using. There will be at least one monochromatic triangle as a subgraph. And what is a monochromatic triangle? That is just a triangle with all edges being the same color, right? So the way we prove this is by contradiction. And so that means that we're going to construct a minimal like a counterexample. And we're going to show that we can't construct this counterexample. So we want to color in a complete graph with 6 vertices so that we don't get a monochromatic triangle. So we're going to start with one vertex and color in its edges. 508, yeah. So by the pigeonhole principle, at least 3 of its vertex edges must be red. And let me know if I need to explain that. Yeah. Could you explain that? Sure. So remember that we're constructing an example here. So actually, should I go over the pigeonhole principle? I think I will. So just the pigeonhole principle is the idea is that if you have, in this case, we have 2 boxes and those boxes are our colors. And we need to fit 5 edges in those colors. That tells us that if you divide 5 over 2, take the ceiling of that, at least one of those boxes must have 3 in it. So in this case, we're putting this, so like for this must have 5 edges, and we need to fit those into 2 boxes. So that means that at least 3 edges must fit in one box. It could be 4, it could be all 5, it could be the same color, but it must be at least 3. And red here is kind of just arbitrary, right? If, like, let's say no vertex has 3 red edges, then it has to have 3 blue edges by the same logic. And this is an important thing that comes up in Ramsey's theory. You can just flip the colors. So red and blue, that's a binary choice, but it doesn't matter which one you assign to which color. So we put down our 3 red edges here. Next thing to do is we actually can look at, instead of filling in these, we jump straight to what happens if we connect these 3 vertices, right? You can see that I put in these 3 potential edges as red. But if I put any of those in, right? If I put in this vertex, we have a red triangle. We don't want that. If I put in this one, we once again have a red triangle. And if I put in this one, once again, red triangle. So none of these can be red. Otherwise, we make a red triangle and we failed making our counterexample. But then we only have 2 choices for our colors. So all those edges must be blue. That gives us a blue triangle. So we've shown that we just cannot make this counterexample. If we have 6 vertices and we color them in with their edges in with 2 colors, we have to have a triangle. Any questions?
So the fact that it's 6 vertices here.
It is. We'll get to that. Anything else? All right. So to answer your question, what if we don't have 6 vertices? And I've written this like 6 numbers of people because we're going back into that party. So what if we have 7? What if we have more than 6 people? Well, turns out we're still fine, right? If you've seen this blue kind of subgraph that I've highlighted here, that's a copy of K6. That's a copy of a complete graph of 6 vertices. So if we have 8 people on a party, or if we have 9, 10, like however much that's more than 6, this property still holds. We're good. But now let's look at 5 people. And okay, give me a guess. Do you think that I can construct a counterexample? And to remind you guys, a counterexample to this theorem would be a coloring of the graph so that there's no red triangle or no blue triangle. All right, I'm seeing one yes. Any other yeses? Any other no's? Yeah. Well, the answer is yes, and we have one right there. Right. I kind of like this counterexample because each coloring is a cycle. Right. You've got 2 cycles of like 5. None of those are triangles. It's kind of cool to see a complete graph. You can just break it apart into 2 cycles. But yeah, so our property holds for any n that's greater than 6, but not less, or greater than equal to 6, but not less. So we have a threshold, right? Any questions on Zoom actually? None so far, but we have a threshold. What kind of threshold is this? All right, and here is the formal statement of Ramsey's theorem. So we'll walk through this bit by bit. Stop me if you guys have any questions. But integers KL greater than or equal to 2, that's really just a formality, right? So blah blah. There exists a minimum positive integer. That's our bound, right? We write it as RKL because that's a bound that we're writing in terms of the numbers K and L. Such that if we color the edge of a complete graph with that many vertices, red or blue, we will find either what's called a red click of K vertices or a blue click of L vertices. Translate that, a click is just a complete subgraph. So our theorem on friends and strangers was R3, 3 equals 6. Because a triangle is the complete subgraph K3. If you think about it, you have 3 vertices, there's only 3 edges that can go between them. That's so a triangle is a complete graph. But you can extend this to 4, 5, right? So you can make this like 4, 4, that's I think 16. 4, 3 would be 9, but like you can change this anyway. Any questions so far? All right. So the proof here uses induction, but I'm not going to go over it because it's kind of non-intuitive. Well, I'll just cover like the basic idea. First, we lay down base cases. For one, remember how I said you can flip the colors? You can flip red and blue at any time. That immediately tells us that R of KL is equal to R of LK. You can just swap them. Yeah.
Wait, what exactly is the statement for previous? I was just finding.
Oops. Sorry, which statement again?
What exactly are you proving here? Isn't that just a definition of what RKL means?
RKL is. That's a very good question. Essentially, what's happening here is that RKL is a number, right? It's written as a function, but it's a number. We are proving that the number exists, it is minimal, and that it is bounded, so it is finite, right? We're essentially saying we have this number that we can study, that we can look for, and that we can calculate. How do we do that, right? So this basic proof, this is just there to be like, okay, it makes sense to ask about what this number is. So continuing on, R K2 equals K. Can anyone guess why this is true? Can anyone kind of like unravel that, figure out what this means? All right, first I'll give you a hint. What's a complete subgraph with two vertices? Or a complete graph with two vertices, what is that? Anyone? Yeah, you can just speak up.
It would just be zero edge.
Correct. So why is R K2 equals K then? If this is saying if I have a complete graph on K vertices, I can either, and I color it in any way, right? I color its edges with two colors in any which way. Either I can find a complete subgraph of K vertices, or a complete subgraph of two vertices, or sorry, a red complete subgraph of K vertices, or a blue complete subgraph of two vertices. How would that be? The answer is because if you color every edge red, that's a K complete subgraph, or that's a complete subgraph on K vertices, that's red, right? That's one case. And any other case, the moment you put in one blue edge, that's a complete subgraph on two vertices. So that's kind of a cheap way to get our base case, right? And then the important thing here is that we're able to inductively define it, right? I won't go over this. The basic idea is just that like these basically give us our smaller complete subgraphs that we can look at, our smaller clicks. And then you just consider, like for one click, you consider all the vertices that the other click added and look at how those connect, right? And you do the same for the other way around. It's a lot of case checking, but the important thing here is that it doesn't actually tell us anything about, it doesn't give us an example. It is entirely non-constructive. So that proves our theorem. And remember that it's non-constructive. Well, remember for right now, because it's non-constructive. So how do we know what these Ramsey numbers actually are? We have an inequality in our theorem. We don't have any equals. So just use a computer, right? Like a basic algorithm would just be look at every possible coloring of a complete graph. And if we don't find the click that we want, terminate, output that, right? Remember that if we find a coloring that doesn't have like a monochromatic click of the size that we want, that's a counterexample to our theorem. And you just need one counterexample to say, okay, the theorem, like the Ramsey number is not this number. And if we check every single coloring and they all have our monochromatic click, we're good. So yeah, let's say we want to calculate R55. This would basically be our program. It's pretty simple, right? But I still see the time complexity is way too big. There are some better algorithms. You can ask me about that afterwards. But even then, there's barely any improvement. So why is the time complexity so big? We just look at the amount of colors that we have. Okay. So the graph Kn has n choose two edges, right? And that's because an edge, you can kind of interpret that as a choice of which two vertices you want to connect. All possible choices, that's n choose two. And keep in mind that is a quadratic. And coloring each edge is a binary choice. So the total number of colorings is 2 to the power of n choose 2, right? So that looks like the complexity then would be, I've written it 2 to the power of n equals 2, but it's really 2 to the power of n squared. That's the complexity that we're looking at, right? And if you're wondering, how big is this? There's n factorial 2 to the n, which we know are pretty slow. This is 2 to the n, this is n factorial, and this blue one is what we're looking at. This red one is a pretty simple simplification you can do. If you shuffle the vertices, you get it like, you can like cut out the colorings that like you get from one time by just shuffling the vertices, but you can see there's barely any improvement. And remember how we are calculating R55? That's between 43 and 48. We know that. So look at how many computations you need to do to determine what R55 is. 10 to the 190. And want to start cracking at that? It would, yeah. It would take us way too long. Oh, that's what we do it. Yeah. Okay. Yeah. All right. So we can set them bound, so we can at least kind of get a good idea of where these numbers are, right? As I said, 43, like R55 is between 43 and 48. So these upper bounds are kind of pretty hard to prove. So I'm just going to present them here. First, these two. These come straight from that recursive definition. If you remember that recursive definition, you can kind of think about unfurling it and bringing it out. And you get a pretty big like truth function. I remember the truth function involves factorial. So this is a pretty large bound, right? What is here? RKK. That is, those are called diagonal Ramsey numbers, where you're just looking for a red click or a blue click which has k vertices, right? They don't have to have a different amount of vertices. So, and those are special interest because those are like easier to study. All right, any questions so far? All right. And our lower bound is square root of 2 to the k for the diagonal numbers. So we have this bound here, and this is pretty much the best known bound that we have. There's been a slight improvement in the upper bound lately. It's on the factor of 2 to the negative 7. It's not great, but it's a good start. It's a really good start. And proving this lower bound uses the probabilistic method. Has anyone ever heard of that? So actually, we can go over it pretty quick. So let's say you want to prove the lower bound. What would you need to find? Does everyone understand what like the lower bound of this Ramsey number would be? Or like what does it mean? Yep.
So like, if you want to prove that this is a lower bound, you would want to show that anything smaller has no example. That's exactly 0 example. So
You just need one counter example.
yes.
Yeah.
Anything smaller has at least one counterexample.
Yep. So yeah, you just want to show that you have one counter example. So what the probabilistic method does, it essentially looks at it, just flips a coin for every single edge to randomly color them red or blue. And all that does is literally say the probability that we have one counterexample is not 0. It doesn't tell you which one, right? It just tells you that there exists one. If you want to search for it yourself, that would probably take you like 1,000 years. I mean, that's the basic idea of the probabilistic method. And if I highly recommend you guys look into that because it actually comes up a lot, right? A lot of times when you're wanting to like get bounds on these big numbers, you bring in the probabilistic method and you see, okay, what's the probability I get a counterexample? And that's how you can put down bounds. All right. Okay, so we're almost done. So any questions so far? Anything you guys want to go back or anything else that you want to explore? All right, so I suppose we'll move on. So we've been looking at Ramsey theorem, right? Now there are 6 other Ramsey type theorems that we can look at. And these kind of form what's called Ramsey theory nowadays. So first, we've had Ramsey's theorem, right? That's the namesake theorem. That's what this entire theory is based off of. Next, and these next 2, I actually recommend you guys go home, search them up, try and work them out yourself. You see what they kind of feel like. Okay, these are actually easier to understand. So one variance theorem. If you color the positive integers, there's a monochromatic arithmetic progression. And we have a bit of extra time, so I'm going to go a little bit deeper into at least these 2. What does that mean? Okay. Okay, unfortunately, you guys only have. No, there's. All right, got it.
The laptop is usually considered.
Okay. All right, yeah. So Zoom, let me know if you guys can see it as well. So the first thing, von der Waerden's, what does this mean? I'm gonna color, this is 2 colors, and this is an arithmetic progression with 3 elements, right? So I'm just gonna color the numbers 1 through 9, red or blue. So I could start with 1, 2, okay, that's actually the point where I should have searched up a counterexample. Right? Okay. Right? Let's say we have that. That's right. 1, 5, 1, 4, 7.
Should 5, 6, 7 right there.
I think the only stipulation is that the arithmetic progressions don't have to be.
So I can't read them consecutive.
Yeah, there's a counterexample, like the one that's trying to see is on the Wikipedia page. I should have pulled it up before I did this. Like they don't have to be consecutive, yeah. Because you have 1, 4, 7, that's non-monochromatic, 2, 4, 6, 3, 5, 7, right? 2, 2, 5. Right, okay, and the question is here. I don't think this is actually the example that they gave. But the question is here, what do we color in 9? Right? If we color a 9 in red, we have a monochromatic. Wait, 2 plus what?
Be 1, 5, 4.
Yeah.
I don't want that.
1, 5, 9. Right? Now we 1, 5, 9. What if we color it blue? That would be which one?
These are 79.
Yeah, okay, this isn't the example that okay. Let me just like yeah, okay, you pull it up. I should remember to bring this. Okay, sorry about that, folks.
I got it.
All right, speed.
Yeah, so 1 is blue.
Okay.
So yeah, what is it? So the 2 red numbers.
Okay.
2 and 3. And then 4 and 5 are blue. And then 6 and 7 are red, 8 is blue.
Okay, that's it. I appreciate it, man. But yeah, the idea here is that if no matter what you color 9 in with, right? If you color it in, like, if you color it in red or blue, you get 3, 6, 9, or you get 1, 5, 9, right? There's no way out of having an arithmetic progression. So that you can pretty easily calculate, but it's going to grow pretty big. And sure theorem is kind of the same idea, right? If we're going back to coloring, if you're coloring the positive integers, and that just means like just slap a random coat of paint on every single integer. right? It's the same idea as partitioning a set of positive integers into a certain amount of energy, into like a certain amount of partition, right? And you always find 3 integers, of which 2 of them add to the next one. They're all in the same color. The next 3 are essentially like, these are actually, the next 3 are actually generalizations of the first 2, right? Rados kind of generalizes both van der Waerden and Schur's. Hale-Stewart generalizes van der Waerden. Rothschild generalizes Hale-Stewart. And you can see they're all about coloring these structures. Like you make a structure, you color it randomly, and you look for some substructure that's not chromatic. And okay, yeah, we're good. So our general idea is that we're finding ordered substructures inside these partitions of sets, and we're partitioning things by coloring them. Or actually, does everyone understand that partition something by coloring it? Does anyone need me to explain that? All right. So, and we want to find bounds for when substructures can pop up, right? Like I showed you, van der Waerden and Schur are trying to partition the first n integers. Ramsey's theory was about how big does our complete graph need to be before we find our complete clips and stuff. Van der Waerden and Schur color the first n integers. And as we saw with Ramsey's theory, these bounds blow really quickly. Van der Waerden's, I think, brings in the Ackermann function, which you guys might have covered in 374. But the Ackermann function is like the first example of something that flows really quickly. Well, Schur too is incredibly hard to compute. So this is the 5th Schur number, right? Like the proof, like Schur 5 equals 161, but to prove that they took 2 entire petabytes of space. This is the largest computer proof that we've had. So like in all mathematics, this is the largest amount of data to compute something.
Isn't that the size of the even monitor in memory?
Maybe
Petabytes is like really close.
it might be, if not bigger. But yeah, and this is literally just for Schur 5. That's the cool thing about the human brain. We can reason about these numbers that we can't actually fit into our heads. But we have ways of writing them down. If you look into Newton's up arrow notation, that gets into some of that. But yeah, I've attached a link here. It's a link so you guys can go into the slides afterwards and look at it. I highly recommend you do, but just for like a tidbit, it's an SAT solver. This is like, they solve this using one incredibly massive SAT solver. And yeah, that's about it. Any questions? Any questions on students? All right, yeah. So that's about it. I'll leave you with one last quote, which kind of got me into this idea. And this is actually attributed to Paul Herodotus. He played a huge role in popularizing this theorem. So, all right. But yeah, Paul Herodotus asks us, what if aliens invade our Earth, invade Earth, and tell us you have a year to compute the Ramsey number 5,5, right? That was Ramsey number for red 5, blue 5, that's R55. And Herodotus says, if we need to compute R55, we could bring everyone together, bring every single computer in the world together, and hopefully kind of get out alive. But if they ask us for R66, we have to attack them back. No chance at all. So that kind of shows just how insane these things get to calculate, how insane these numbers are to calculate. The amount of computational effort that would take to prove R66, which is not that far down the sequence, is more than what we could ever hope to imagine. But yeah, that's about it. That's the entire presentation. Thank you.
Thanks all for coming. Next week we'll do some combinatorial game theory. And then the week after that will be a scheming algorithms presentation by our friend Ryan. And then the last presentation will be Jeff Harrison giving this presentation. So that'll be the week before that. We don't. Yeah, thank you all for coming, and then thanks again for putting this together.
And yeah, so feel free to check this out, like, if you're wondering about algorithms, you click this, and of course, your textbooks that you.
Thank you all for coming.
Get all of these uploaded.
Yeah.